Okay, so we have our null hypothesis that the M&M Mars company is telling the truth. They have 20% blue in their bag, so null hypothesis is P equals 0.2. And we're only interested in is it different from that, so we're going to use not equal to. Okay, if we're not given an indication of whether it should be higher or lower, then we use not equal to, which makes it a two-tailed test, and we'll look at how that changes things. Now, the next step is to check our conditions. Now I can guarantee you that I was not in Stater Brothers numbering the bag of M&Ms from 1 to however many were on the shelf and randomly selecting a bag of M&Ms. So I left my calculator in the classroom. Because I don't believe that it really matters. The bag that I picked, there's no reason it's first on the shelf, right? There's no reason it specifically went to that Stater Brothers. There's no reason it was specifically shelved right before I bought it, right? So it's probably pretty representative of every other bag of M&Ms, right? So although it's not a random sample, say the bag of M&Ms is representative, yeah, of all bags of M&Ms. I always love, when we get to chapter 24, 25-ish, we do an Oreo experiment. Yes. And I end up having to check out with like 6 packages of regular Oreos and 6 packages of double stuffed Oreos. And I'm always like, it's for an experiment I'm doing. I don't just stock 12 packages of M&Ms in my house. And then they're always interested in knowing, well, what's the experiment? And I say, well, we're going to test to see if the double stuffed Oreos are really double stuffed. I'm not going to tell you. You are going to find out when we do the experiment. Although I do tell the checkers because I figure they're probably not going to do it on their own.
I think the double stuff aren't, but the triple stuff actually are.
Triple stuff. So we have another food day to look forward to, right? Okay. So our p hat was 107 over what? 557? So 557 is less than 10% of all M&Ms. Yes? Okay, that's reasonable. We're talking about all M&Ms in the world. We're good. When we are doing the hypothesis test, we need to check to see if given our sample size and the hypothesized value, would we expect 10 or more successes and failure based on our hypothesized proportion. So that means NP is greater than or equal to 10, and NQ greater than or equal to 10. I have to use the 0.2. So 557 times 0.2 and 557 times 0.8. Okay, and so these are the little nuances that we have to remember, right? And I just forgot right before this of that nuance. And make sure you actually do the math. 557 times 0.2. We're going to say 111.4.
What happens if you don't write the NP?
If you go straight into the numbers, that's fine. But you have to write the 11.4 and the 445.6. So we have 4 less M&Ms than we expected. And then again, now since conditions are met, a normal model is appropriate. I will use a 1-prop z-test. Okay, and my p hat is 0.192. Now, if I was going to draw this normal model, no, but I want to show you what I mean by a two-tailed test, okay? So there's 0.2, the standard deviation is the square root of 0.2 times 0.8 over 557. I'm using the hypothesized value for all of my p computations. I get 0.017. So one standard deviation here is 0.183 and 0.217. And 0.19 is about here, right? So this is the area I'm looking to find, but because I'm interested in only if it's that far away, either greater than or less than, I'm also interested in the same distance greater than. This is what a two-tailed test means. My p hat is 0.008 away from the mean, and I'm interested in what's the probability of getting something that's 0.008 less than or greater than the mean, and so I want both sides of that tail. And we're just going to calculate the one, and because it's symmetrical, we'll times it by 2.
So is this true of anything that has the alternative hypothesis as not equal?
Correct. This is the way it is for all not equal to alternative hypotheses. Struggling to speak all of a sudden.
She's nervous. Because she knows she's going to get more viewers on the YouTube channel.
Okay, so remember that my z-score is the p hat, my sample, minus my hypothesized value, divided by the standard deviation of the hypothesized proportion. 0.192 minus 0.2 over 0.017. Yes. This is not different from my other example. I just had already calculated the square root in the denominator here. I already did that right here to draw my model. So instead of putting the square root on the bottom, I just put the number. So this is the square root of p naught q naught over n. Okay. I just calculated it ahead of time, so I'm not going to recalculate it. And now that's normal CDF. Negative 99, comma, negative 0.471. It's less than the 0.9192, right? Because this is less than. For my two-tailed test, I have to pay attention to what the sign of my z-score and go negative if it's negative and positive if it's positive. If I do positive 99, I'm going to get over 50%, and then I'm going to end up with over 100% when I multiply it by 2.
Oh, gee, oh my, this breakfast has got to be delicious.
And then we're going to times by 2 because it's not equal to.
So we do times by 2 because both sides are symmetrical and it's like
Exactly. Both sides are symmetrical, so I only need to calculate one side, and it'll tell me the area on both directions, so I'll just multiply it by 2. So there's a 63% chance of getting a sample of 0.192 if the true proportion of blue M&Ms is 0.2, which is pretty darn likely, right? So we're going to interpret our p-value. If the true proportion of blue M&Ms is 0.2. This is our p-value. I'm going to interpret it right now. This is what it means. When we interpret the p-value, this is what it means. It means if the true proportion of blue M&Ms is 0.2, there is a 0.638 chance of obtaining a sample proportion as or more extreme than 0.192. The p-value is the probability of getting our sample proportion if the true proportion is our hypothesis. So it's really likely that this difference is sampling variation, because of course the machine isn't going to count 20% every single time, right? It's going to be close, right? So it's the probability of getting that, and that's likely sampling variation, the difference. Robin? So here's my conclusion for this problem. Since my p-value of 0.638 is so large, I fail to reject the null hypothesis. There is not enough evidence to convince me the proportion of blue M&Ms is not 0.2.